Welcome to Walkabout the Galaxy, the tangential astronomy podcast, where the science is universal, the opinions are personal, and the topics are occasionally topical. We are strange, charm, and up the astroquarks, also known as Josh Caldwell,
Addie Dove,
and Hannah Sargent.
Coming to you from tiny little squares on our computer screens. Remember to subscribe to us on all platforms, including YouTube, Facebook, Twitter, and Instagram. Our YouTube videos now feature more engaging thumbnails and descriptions because I am no longer writing them. We are also at www.walkaboutthegalaxy.com, where you can see how to order a Walkabout shirt and support STEM education at the same time. You can email us anytime at wtg@ucf.edu, and be sure to email us that way if you order a shirt to make sure that not only do you get it in a timely fashion, but in any fashion at all. Our stumper today, apologies to Hannah.
I know some things.
Who knows some things. She does know some things.
I like that out of context.
Our stumper today, we were mentioning, we were talking about nerd news earlier, mentioning the Obi-Wan Kenobi series, which has just wrapped up shortly before we recorded this. And so, Star Wars and the Force, and there's some new Star Trek shows out there too, and Vulkans have some kind of cool stuff. So your stumper today is the Force, the Star Wars Force, whatever the heck that actually is, or the combination of mind melds and Vulkan nerve pinches.
Okay.
So I feel like I know what a nerve pinch is, but what's a mind meld?
Oh my gosh. The Vulkan mind meld.
Where like Spock
Vulcans,
does
they go up to you and they put their fingers on you, and then they kind of merge with your thoughts, and they know what you're thinking.
Oh, okay. Yeah, cool. Right, I'm on board.
They do that in a sort of a different way, I felt like, in Strange New Worlds, in one of the episodes of that.
I'm sure they did do it differently because they got to change stuff. So,
yeah. There's also,
we even see in one of the original series episodes, Spock puts his hand up on a wall, and there's a bad guy on the other side of the wall, and he's able to like make that bad guy think, oh, I better go through the door, So it's got some sort of quasi Force-ish aspects, but only with regards to like knowing or mildly influencing what other people are thinking. There's no like, making boulders go fly around or anything like that.
Yeah,
I'm pro Force. I think that's where I'm at. Yeah, especially in like in a COVID era, it's just nice not to have to touch things and just not have to go near other people. Yeah, that's right. I think I'm a fan of that.
Okay, Addie, what about you?
Yeah, I mean, the Force is definitely a much more expansive property, right? Because it is sort of a mix of telekinesis and
telepathy.
Yeah, telepathy / something like that, right? Whereas the Star Trek stuff tends to be more, I think, right? Tends to just be more brain and
more acute as well.
Emotions and
I threw the nerve pinch in there so you could at least knock somebody out, but yeah.
Sure, that's true. So I think I'm going to go Force.
Yeah. Plus, who really wants to know what other people are thinking, really, anyway?
I feel like they could use it to influence, like you said, right? He can use it to influence
the influencing
which
thing
they also do with the Force sometimes.
Yeah, we saw Obi-Wan Kenobi do that in one of the movies where he's like, you're going to go home and explore your life decisions or something to some drug addict or something.
These are not the droids you're looking for.
Exactly.
Right?
Yeah, yes. Yeah. So, all right, we'll give this one to Star Wars then over Star Trek. Well, today we'll talk about a couple of small objects in the outer solar system with funny hats. Charon, which has a red hat, moon of Pluto, and Arrokoth, which has a scruffily hat, but we're really going to just be talking about Arrokoth, which is this funny gingerbread cookie-shaped
snowman
thingy in the outer solar system. But first, this episode of Walkabout the Galaxy is brought to you by the phase function. You may have some smooth moves on the dance floor, but if you want to get your electromagnetic radiation scattering perfectly lined up too, you'll need the phase function. Available in different configurations to match your surface, the phase function is your one-stop solution to determining the reflectance of an object under any viewing and lighting conditions. Quickly and easily use the phase function to check for forward scattering and back scattering. For a small additional fee, enhance your phase function with the opposition effect. We're sure you'll have no opposition to calculating brightnesses with the phase function. The phase function, sense and simplicity.
Ooh, sense and simplicity. I feel like that's
Sounds like a Jane Austen novel.
It is. I feel like it's like an electronics thing.
It is an electronics thing.
Like Philips or somebody that does.
It is Philips.
Oh my lord. How'd you manage that?
I am astonished. That's like getting the Wordle on your first guess.
Oh my gosh, I know. One day, I always use the same word, so one day it's going to happen.
Do you know what happened to me?
It did?
Yeah, I didn't know anything about it. It was just, I have probably 10 or 20 different words I do for the first guess. And I just got lucky.
Oh man, which day?
Lucky. Train, Train was the word.
Okay.
And I just happened to do it. So my dad was a model railroad guy, so it was for dad.
Aw.
So yeah, Phillips. Wow, I'm impressed. Not only is it impressive enough to get that, but it's not even there. It's they have retired. That's their retired slogan.
Nice.
Their new slogan is "Innovation in You."
Oh, okay.
But I like Sense and Simplicity because of that Jane Austen throwback.
Yeah.
Fallout.
Agreed.
So, we have at least a couple of interesting bits of space news.
Yes. So, actually, I was ashamed that I didn't even know much about this one. So the first one, the Capstone Mission. So this is a mission to the moon, and it's supposed to launch today, but it's been delayed until tomorrow. But that's not a significant delay, really. And it stands for the Cislunar Autonomous Positioning System Technology Operations and Navigation Experiment. Basically, it's going to help out with the future Lunar Gateway Artemis program type stuff. So one of the big issues that we're going to have is communications and navigation when we're not in direct line of sight to the moon. So it's kind of sorry.
Go ahead.
So yes, I think it's going to be testing out some inter-spacecraft communications and things like that, which will need to be done when we're say in the lunar poles or on the far side of the moon and things like that. And so this mission, I think it's only like a CubeSat, like the size of like a shoebox type thing.
It's a pretty. I don't know the physical dimensions, but it's like over 50 pounds. So that's bigger than outside the standard sort of CubeSat shoebox mass limits, but still it's a tiny satellite.
Yeah, so with CubeSats, which are these sort of 10 by 10 by 10 centimeter cubes, you can then stack them up in like modular ways. So they've called it a microwave oven-sized CubeSat.
Okay.
And so it's going to take a 4-month journey to the moon. Bearing in mind, if you take a straight line, you can get there in 3 days. So they're obviously,
or even less if you're going faster.
If you're going, yeah, true, yeah. So this is quite a relaxed sort of mission to the moon, and it's interesting because they can launch any time between now and I forget, is it sometime in July? But no matter what day you launch on, you will still get there on the same date in November.
Huh.
Okay.
Yeah.
So is it doing one of these sort of gradually spiraling out sorts of things? And what's the propulsion that it's using to boost the orbit? Is it
good question,
like ion or something like that? I mean, with such a slow trajectory, it's something that's going to be a very gentle thrust. And some of these smaller CubeSats I know use ion engines, right, Addie, where they're basically accelerating tiny, tiny, tiny amounts of mass out the back end, out the rocket end of your little CubeSat, but at very, very, very high speeds by using electricity, essentially, to accelerate ions out the back as that's the momentum going out the back end so that you get some momentum going in the direction you want to go. But because the mass is so small of your fuel, even though they're traveling at very high speeds, the change in velocity for your spacecraft is pretty small.
Yeah, I'm trying to quickly kind of search on this, but I'm struggling to get answers.
Yeah.
This,
In any
Yeah, it's
event,
interesting. So part of it is that this is a mission that so it's like a small spacecraft, and it's like built by a small company, and it's going to be launched by Rocket Lab in New Zealand. So like it's like NASA paid for all of this, but like it's not a NASA built spacecraft.
okay, so it's like a NASA contracted to have this test done for some technology advancement.
Yeah.
And yeah, you were mentioning the gateway. So the gateway is this thing that is yet to be built and will not be used on the first couple of human missions back to the moon, right? The gateway
yeah,
is
it's supposed to be kind of like some sort of orbiting station around the moon, and I think they want it to be human tended, so not permanently crewed like the International Space Station is, but this station that can have effectively visitors to come in and work there and do what they need to do. And it has a really interesting orbit. It's called a near rectilinear halo orbit, or NRHO. And so the Capstone mission is going to also go into that same orbit. It's like this really elliptical, so it goes really close to the moon and then loops out really far away.
right.
Um, I think over the top of the moon, if that's right, like north to
Yeah,
south.
I think that's right. I think the close point is over the North Pole of the moon, if I recall correctly. I had a student who was studying the potential blasting of the lunar gateway by moon dust kicked up by the giant starship coming down to land on the surface of the moon, and with its engines and this low lunar gravity blasting all of this dust and dirt up into space. And some of that could then hit the gateway spacecraft. So we had that orbit simulated there. So that's sort of an eventual sort of transfer station for astronauts to go from the thing that takes you from the Earth into the thing that takes you to the surface of the moon and back again the other way. So, well, that'll be exciting to follow that mission. And what was our other?
Yeah, and it's
Um,
going to be the other thing about that one is that it's going to be testing some like communications technologies. So it's going to be communicating with the Deep Space Network, which is how a lot of our satellites that are in space communicate with Earth. But it's also going to try sending signals to LRO, the Lunar Reconnaissance Orbiter
okay,
spacecraft, to do spacecraft to spacecraft communications. And it has an atomic clock on board to test like its own positioning and timekeeping, which is some sort of advanced technology that's being tested for future spacecraft. So it's got some cool um, features to it. But I
cool.
actually still don't know what its propulsion is.
No.
I'm guessing ion engine, but I'm just guessing. So we'll.
Yeah, agreed.
Um,
And I think
but
as well
yeah,
it's is it Astrolab? Is it
the communication is going to be a key thing because, as you were mentioning, Hannah, at the beginning, that the moon gets in the way. It's this, we're on the Earth is rotating, of course, and then you're dealing with stuff that's orbiting the moon and eventually people and stations on the surface of the moon. And there's no way that all of those things all the time are going to have clear, direct lines of sight between every two sets of things. So lots of relay stuff will have to be going on.
Yeah, China put a relay satellite up before it put its mission to the far side.
Right.
And that's in a funky orbit too. But
and yeah, and sorry, I think I got the name wrong. So it's Rocket Lab's Electron rocket that will be launching this
Right.
yes,
from New
from New
Zealand,
Zealand.
hopefully tomorrow morning.
And BepiColombo is
Yeah.
BepiColombo. Yeah, so this is the other bit of space news, or sort of updates, I guess. The BepiColombo mission to Mercury, so it hasn't arrived yet, but it's done a flyby of Mercury, so it must be so sort of like tantalizing to the people involved. So this is a mission that launched in like 2018, and it has this really interesting journey to get to Mercury. Sorry, I think it's like 7-year mission to get there. And yeah, so this is a joint ESA and JAXA, so European Space Agency and Japanese agencies. And so yeah, as part of this journey to get to orbit around Mercury, it has to do a series of flybys, which allows it to sort of slow down in order to end up in a nice steady orbit around the planet. And in this flyby, they test out some of their instruments, and we've got some nice images back as of Friday, I think it was. We got these images back, and the camera works, so people are happy. But it's got this really weird setup. So it's got like some of the payloads, or I think the spacecraft ends up like opening up or splitting into two or something, and so some of the payloads aren't yet exposed to like the outside, so they can't be used. So they've only got a limited number of instruments that they can access at the moment. But the images look really good, and I kind of forgot how cratered Mercury is compared to the Moon. It's a mess.
And
this was its second gravity assist. Sorry if so it's like so it's doing these cool different. I think it did one. Didn't it do one by Venus?
I feel
like it got us
a much. I took a look, and the image of Venus was kind of like this small bright dot in the background. It wasn't anywhere near as close as these flybys are. But yeah, it's this really interesting journey. So they have to go to quite high speeds to get sort of into the inner solar system to get near to Mercury, but then they almost have to exchange energy with these planets and slowly slow themselves down.
So it had an Earth gravity assist a year and a half after launch. Then it had a Venus gravity assist six months after that, and then a second Venus gravity assist, and then Mercury gravity assist. And it's you're talking about like how long it takes to get from the Earth to the Moon, and it depends on how you get there. Mercury is like right next door in terms of like orbital distance. It's less than 1 AU separation between the orbit of Mercury and the orbit of the Earth. It took Cassini 6.5 years to get from Earth at 1 AU to Saturn at 9.5 AU. It's taking the same amount of time for BepiColombo to get from Earth at 1 AU to Mercury at like 0.38 AU. And that's because
you can't just go there.
You can't just go there because you're always orbiting the sun, and the sun is the big bully. And the closer you get to the sun, the more it matters, and the more the difference in your orbit matters. So that 0.7 AU difference between Mercury's orbit and the Earth's orbit is a much bigger deal than, say, the difference between 8 AU and 9 AU out in the outer solar system. So the amount of energy change that spacecraft has to have in order to get into that smaller orbit is really, really big. And then you only have these pipsqueak planets like Earth, Venus, and Mercury to do these gravity assists with, whereas if you're going to the outer solar system, you can use Jupiter to really
Jupiter's got a lot of gravity.
You can exchange a lot of energy between the spacecraft and the planet more easily that way. So yeah, it's always ironic and somewhat counterintuitive initially how long it takes to get to the inner solar system and to Mercury in particular, especially if you want to go into orbit around it. Because as you were saying, Hannah, you can like fly by Mercury, that's no problem. You go zipping by. To like slow yourself or match the orbit of Mercury so that you can go into orbit around. It's a whole different story.
It was actually really nice on when the pictures came in. So I was saying earlier to you both that I was at the British Planetary Science Conference, and a number of the science team were there. So they ran off to go get these images, take a look, and then we had the conference meal. So we all crowded around their phones looking at these first images of Mercury. So yeah, it was a good night.
That's funny.
Nice.
And it's, just sort of funny now, everybody's sort of crowded around their cell phones to see these latest results, and think back, whatever, 30 or 40 years ago, it would have been at big old CRT monitors at JPL that you would have been crowded around.
It makes me wonder when we actually make it, and for after the 7 years are up and we're in this nice orbit, I wonder what we'll be crowding around then to see those images.
They'll be on our heads-up displays on our on our cool Google glasses.
Oh no.
Well, in honor of our sponsor today, I give you your trivia questions now, before we go into our two science stories. In honor of our sponsor, the phase function, today's trivia questions are about reflection. and they're pretty straightforward. They're not.
Do we have to think a lot about these?
No.
Ah, that was a reflection joke.
Oh,
Never
it
mind.
was too subtle for me. I didn't think about your joke hard enough.
The high albedo.
What is the most? So here, it's going to give you several questions. What's the most reflective body in the solar system? And what are its bond albedo and visual geometric albedo? So I'm going to define a few things here for you. So the phase function, our sponsor paid extra for this explanation, says how reflective is something depending on the viewing geometry that you're looking at it compared to the direction that the sunlight is hitting it. So if you got the sunlight behind you and you're looking at the objects, you're sort of looking at the full moon, for example, that's at zero phase. And if you're looking at a crescent moon, you're looking more at a high phase angle. So that variation in brightness is what's described by the phase function. The bond albedo is the total reflectivity accounting for all different wavelengths of light. So all the light that hits an object, it's all the light that's reflected off an object divided by all the light that hits an object. So if something truly reflected every incoming amount of light at every different wavelength from, X-rays to radio, that would have a bond albedo of 100% reflective. The visual geometric albedo is how reflective is it at that full moon geometry compared to our previous sponsor, the Lambertian surface. So that number can be greater than 1 because so a mirror, for example, the Lambertian surface is like a movie screen. And if you were looking at a mirror, it's going to straight on with a light. It's going to reflect more light back at you than a movie screen would under that same geometry.
This trivia requires a lot of work.
It is. Somehow it didn't seem like it was that complicated when I was drawing it up. But it isn't that complicated. It's more complicated to explain than it is to answer. So which object is the reflectivist, the most reflecty object in the solar system, and how reflecty is it?
Okay.
And we'll have
much. That's it. Oh,
well,
it's a single,
the follow-ups are very simple.
Okay.
I can't wait to hear you explain these questions again the second time around.
I'm not gonna.
Oh no.
No. Okay. So let's work our way out in the outer solar system, starting with Charon, Pluto's moon.
Yeah, we're very solar system centric today again. We're very solar system centric today.
Yes,
but we were talking.
We're topless, so we don't have.
We were talking earlier about how Mercury has to do all these shenanigans to get into orbit around, or BepiColombo has to do all these shenanigans to get into Mercury orbit. But New Horizons spacecraft was one where we just flung it out in the solar system and said, "Go, be free," and it's been running away from us ever since at really big high speeds.
Yeah.
But that allowed us to fly by Pluto, and then it flew by a body called Arrokoth after that. But when it flew by Pluto, we got all this really interesting data about Pluto, obviously, and its moon, Charon. And so there are some new, a couple of new papers out that are looking at some of these interesting sort of chemical, but also reflectance features, actually, since we were just talking about that show that there's these interesting hats on it. There's an interesting hat on Charon. So one thing important to know about Charon is that it's like its spin orbit and the way and like how it faces the sun make it sort of wonky. It's all tilty with respect to its orbit.
Yeah, Pluto's kind of like Uranus, I believe, in that it's a very tilted system.
Yeah.
And Charon, so Pluto has at least 6 moons. Charon is the largest by far of the 6 moons that
one we've known about the longest.
Yeah. And because Pluto and Charon are not, they're the closest in sort of mass ratio to each other of any planet and moon in the solar system. So some people refer to it as a double planet. Um,
Mm-hmm.
we're all familiar with the fact that the moon always has one face facing the Earth. That's because tidal forces have slowed the rotation of the moon so that its spin matches its orbit, and we always see the same face. So it's like, if you're dancing around, someone you love, and you always are facing them even as you go around, but you're still spinning yourself. That's what the moon does with the Earth. And the Earth is in the process of slowing down to reciprocate that to the moon, but because it's so much more massive, has so much more spinning momentum, it's not going to get there. But with
Yeah.
Pluto and Charon, they're both locked into each other. They always have the same face facing each other. Not only, that's right, not only is Charon always pointing the same face towards Pluto, but Pluto is pointing the same face towards Charon, and then they're tipped on their side, which makes these
Yeah.
very extreme seasons.
Yeah. And so they have really strange seasons. There's also interesting dynamics between the two. So Pluto, so there are seasonal effects due to like atmospheric release from Pluto. There's things like methane and ethane that actually get transferred from Pluto to Charon, probably. So there's sort of seasonal exchanges of material that then can get deposited on Charon's surface. And so there's these interesting observations from one of the cameras on board New Horizons. It's the MVIC camera, which I don't multispectral visible imaging camera. So basically, it's imaging in visible light we can see, and that said that there's sort of a red polar cap on Charon, and there's actually some observations from looking at reflection and Pluto shine in the South Pole indicate that there might be a southern polar cap also. Um, and so there's this interesting sort of red material deposited, a little hat on Charon. And the question is like, how does it get to be there? And an older hypothesis was that it's an impact feature. And so it's something sort of deposited in this impact, but it's hard to sort of explain how you'd get it at both poles if it's an impact, right? And much more likely is things we see on a lot of other planetary bodies, right? Which is that it's a seasonal effect where you get deposition at the polar regions. And so there's a couple of new papers that we're working on, like sort of interpreting these observations and seeing how you can get this reddish color and how it might be deposited in these polar regions and then retained.
One of the interesting things, you mentioned methane and ethane. So these are things that are gases in our everyday experience, but it's so freaking cold out there that they can
Yeah.
be ices at those temperatures. But they're like super volatile. They don't really want to be ices. It doesn't take much energy to heat them up. So ethane are what are lakes on Saturn's moon, Titan, lakes and rain and stuff like that. But at Pluto, they can be frost. And so so Pluto and Charon, I mentioned they're tilty, but also it's a very egg-shaped orbit, which means that there's very extreme seasonal change as well, and they have very, very tenuous atmospheres. But when it's close to the sun, it's enough warmer that those very volatile things like methane and even nitrogen, which is icy out there, um, evaporates, sublimates, and gives you this big increase in atmospheric pressure. And once you throw a tilt into it, you can get a very sudden transition from I've been in nighttime with no sunlight for like over 100
A
years
long time. Yeah.
because the orbit is so slow. And then all of a sudden the sun peaks above the horizon. And you know what it reminds me
Vampires
of?
would love it, except when you have that sudden transition.
Who would love it? Vampires. But,
Vampires. Yeah.
but you know what that sudden transition reminds me of?
The moon.
No, the landmark movie Deep Impact, where the sun
Oh,
rises on the comet, and as soon as the sun rises on the comet, the
yes.
ice starts evaporating, and it has all sorts of dramatic,
Yes.
exciting effects.
Which
Excellently
material can be
depicted.
red though? What material, when icy, gives
Uh,
you that red
well,
color?
that's the interesting thing, though, is
So
because it's
that's
more complicated than that, right? So
yeah.
so you have this seasonal thing where all of a sudden the sun rises, and then this stuff evaporates, and it poof pops off one pole and recondenses on the other one. And then you have an exposure of this material to
Higher
solar
energy.
radiation and charged particles that then
Mhm.
processes things. And it's the
You could also
processing,
get exposure to like Lyman alpha that can
right?
do some of the photolysis as well. So high energy UV light, and then also, like Josh mentioned, solar wind charged particles um, can interact with the methane and cause this reddish hue.
Yeah. So you have to have it's a complicated story that involves um, not only the sort of sublimation exchange, but also um, space weathering processes on the material after the fact. And very generally, they did a lot of computer simulations. They also did some laboratory modeling. This is Southwest Research Institute, and one of the authors on the paper, Randy Gladstone, is somebody I worked with at last when I was my first year in grad school. Helped me out with a paper.
Aw,
Um, and but basically, space weathering tends to make stuff red because what it tends to do is knock hydrogens off and leave carbons behind, and that typically gives you some sort of red spectral slope. And in detail, this is more complicated than that, but we don't go into those kinds of details except for the trivia question.
yeah, of course.
Oh no. Is this preparation?
No.
So that's kind of cool. And then yeah, so I would they sort of refer to this sort of like explosive change, explosive seasonal change in Charon's atmosphere. Of course, the atmosphere is next to nothing,
Yeah.
but it gets a
So it's
thousand
like you get
times.
two more molecules and it's a pretty explosive
That's right,
change, but
but it does get as much as 1,000 times increase in atmospheric pressure with these, potential seasonal evaporation events of these polar deposits. So that's
So,
kind of
when are those seasonal changes? Because obviously this orbit is massive, right? So we're talking
yes.
hundreds of years. Is it in our lifetime that we'll see a seasonal change to check it
I
out?
don't think so because, and also part of this whole. So I don't think so. So it happens at Pluto and Charon's equinoxes. So not at the solstice. So not when the sun is highest for the pole, but when the pole sort of first catches a glimpse of the
Yeah.
sun over its horizon. But I don't know when that is. So you
yeah.
stumped me.
I'll take that.
We'll have to check that out. It's a 248-year orbit, so that means 124 years between equinoxes. So there's a good chance, Hannah, that you at least
One
will
of us,
have,
maybe. No,
will have a Pluto equinox in your lifetime. If I haven't had it already, which
The
maybe I
most
have and I
recent
missed it,
Pluto the most recent Pluto equinox was in 1989.
89.
So it was just before me, I'm afraid. You guys were lucky.
Yeah, but we didn't know about this.
You
I
didn't know
wasn't looking.
about it. You weren't looking in the
And
right place.
its perihelion was 1990.
Okay. Yeah, I knew that perihelion was soon because that was one of the arguments for New Horizons getting to Pluto now rather than waiting 10 or 20 or 30 years because it's just overall getting colder. So
Yeah.
any atmosphere it has is recondensing onto the planet Pluto and the moon Charon. So they did want to get there early enough to like catch an atmosphere. Um, and I was aware of that, but the equinox I didn't know. But as I said, I missed it. I wasn't paying attention in 1989. Okay, so even further out, you mentioned New Horizons. We flung it out there. We set it free. It must not
We
love us
did.
because it's not coming home.
It's
And
still sending information.
but it does love us enough to send us some interesting information back. And the next object it flew by is this object in the Kuiper Belt called Arrokoth, which is about 30 kilometers head to toe.
Long.
And
Yep.
head to toe is maybe not a bad metaphor to use because it's sort of like a snowman kind of shape, a small circularish blob on top of a larger circularish blob.
Yep.
Um, and so there's a really extensive analysis of like every aspect of this object in a new paper by the New Horizons team. James Keene is the JPL is the lead author, and the density, the the moment of inertia, the smoothness, the slopes, the jaggediness of it, the gravity, every different kind of thing you can imagine has been very carefully extracted
Modeled.
from the New Horizon and modeled from the New Horizon
And
data.
it's pretty tough to do, right? Because we were talking about earlier how fast it's going. So we only have a few images basically of Arrokoth. And this was one of the big challenges is we had some models before we flew by from doing ground-based observations, but like actually getting the data back, it was like it looked similar but different than we expected. And at first we thought it was a snowband, but then it turned out it was flatter than that. So it's more peanutty now. And so yeah, but so getting all of these parameters, you have to make a lot of assumptions based on what we know
Right.
about other comets and asteroids, about other things, and how the material behaves on their surfaces and how they're shaped like they are.
Yeah, it's sort of like you say, well, I don't know for sure what it's made of, but if it's made of these other things that are out there that this is probably similar to, then I can infer this about the density or the mass of the object. So the density of this is one surprise. So
They infer the density is way lower than they expected.
yeah, they were thinking it would be like a comet. The one comet that we've got the density nailed down exactly is 67p.
Mm-hmm.
That's the comet
See,
that
I find that interesting because it's it presumably if it has this snowman shape thing, it looks like these two objects that have kind of attached together, which was similar with 67p. They called it the rubber duck because it had the
right.
head and the body, and
Yep.
yeah, so they must have had just the same levels of forces and densities and speeds and everything that's
Yeah, and
going on.
it's also interesting as you mentioned. They're morphologically similar. They're both icy objects, and we have to put the caveat that for this object, the density is very uncertain. Their sort of nominal value is about half the density of 67p. The density of 67p is about 0.5 grams per cubic centimeter, so half the density of an ice cube, which is
Yeah.
already not very dense.
Yeah.
This one, their nominal density is a half of that, or about a quarter of the density of an ice cube. But it does have a big uncertainty because they had to make some assumptions. So it's
Yeah.
possible that it is as dense as 67p.
But that would be
But
on the upper end of the range.
that would be at the upper end of their uncertainty.
Yeah.
Another reason that's a little bit surprising, this object's much bigger than 67p. And you sort of, as objects get bigger, they tend to scrunch in
Get more dense.
more.
Yeah.
So that's an interesting discovery. It also, for other objects in the Kuiper Belt, we do have known densities because we've observed lots of binary Kuiper Belt objects that orbit each other, and from that you can get a mass and a density from those a little bit better. And this is less dense than those bigger Kuiper Belt objects. Makes sense that those bigger ones would be more dense than this, but very low density, which means it has a very weak gravity. So it's
Yep.
sort of like snow. It's sort of the density of snow.
Yeah.
So
You
it's
know,
cute having a
Which like
snowman
so
then.
it's a really unprocessed solar system body, right? So we talked about that Comet Interceptor mission that wanted to intercept a sort of primordial body previously, but like so this is like probably hasn't had a lot of processing. So it could be sort of this ancient looser snowball and
right?
still be intact, partly because it hasn't had as much processing and dynamical interactions and things like that potentially.
Yeah, hasn't been battered very much. And one of the other things that sort of comes back to that also that I thought was interesting is that the you can define for any sort of three-dimensional object, you can define three principal axes. So think about a brick. There's the axis through the long end of the brick, there's the axis through the middle dimension of the brick, and then there's the axis through the top of the brick, the short axis. And for these two blobs on Arrokoth, the axes are all very closely aligned to each other. Only, much like 1/100% chance that they would align that way by chance. So that suggests that the fact that they're aligned that way has something to do with how they came together. And because they're so fluffy, snowy, they probably came together in a very gentle way, and they may have been sort of interacting with each other to get their axes lined up somehow before they stuck together. So there's lots of interesting clues there about how objects in this sort of 10, 20, 30 kilometer size range form, which are the precursors to planets. So pretty cool.
Yeah, and they do a lot of, so they figure out sort of what its rough density would be. And when you do that, when you have like its sort of shape and its density, you can figure out like what the acceleration will be at different places on the surface. So see where there's like sort of low and high regions due to acceleration, right? So like also due to geography, but then you can also sort of see where the low acceleration points and the high acceleration points are, and see where things would tend to like fall on the body, which is often counterintuitive.
Right. Yeah, for these odd-shaped tiny objects, down is not always down. Sometimes it's sideways.
Yeah. There's a couple of good Easter eggs, Josh, in the figures in the paper, in figures 7 and 8. If you zoom in and enhance it, there's actually an Enterprise D for scale.
Oh, that's awesome.
That's like one grid cell size, basically.
Oh, wow. Oh, there it is. That's amazing. That's amazing. Hats off to the authors of the paper for that.
So they get some really cool inferences about sort of its dynamic behavior, where things would be on the surface, how material might move around. It's a pretty cool, and lots of pretty pictures then of their modeling.
Yeah, very, very thorough analysis. And then we hope that we will see, more objects like this in future missions to the outer solar system, because this really gives us, some unprecedented insight into how planets form. Yeah, their caption, yes, does indicate that they include the Golden Gate Bridge and the USS Enterprise D for scale. That's awesome. I wish I had a cool segue from that back to our trivia, but I don't.
Oh, no.
Although one of the follow-ups will consider Arrokoth.
I forgot to mention when we were talking about Charon, actually, sorry to throw this back, but it's the name of the region. It's called Mordor Maculus.
Wow.
Yes.
And I just forgot to mention that. I was so excited about that. But it's a pretty awesome name and pretty terrifying.
We'll have to have a stumper having to do with Mordor and something else.
Excellent.
Terrifying. Mordor and the Upside Down.
Oh.
For two things I don't know very much about. Okay. What's the most reflective object in the solar system? We'll start with Hannah Sargent.
Enceladus.
Addie, what do you think?
That's a good guess.
You can guess the same.
I think I might guess the same. We can either be wrong or right together.
You are correct together. It is Enceladus with all of its freshly fallen snow. So now the follow-up though is, how reflective is it? So what's the total, all the light reflected off Enceladus divided by all the light falling on it? What's that ratio? That's a number less than or equal to 1.
0.75.
I was going to go 0.7.
You can.
Yeah, do it. Yeah, 0.7. 0.7.
Okay, edges to Addie for this one. It's 0.81.
Okay.
Nice.
Yeah. For the visual geometric albedo, I'm just going to tell you, because that ended up being such a complicated thing to explain, and I don't even know if it made any sense. But its visual geometric albedo is 1.38.
Oh, wow.
That was going to be my guess.
Shoot. I robbed you of the opportunity to dazzle us with your brilliance.
I still don't even know what the question was.
Well, it's just okay. Don't worry about it.
No, I'll figure it out.
You can replay the episode. And
I shall.
What planet has the highest bond albedo? Is the most reflective? That number of 0.81 for Enceladus. Which of the planets, including Pluto, has the highest reflectivity?
It's just confusing to me because, like, atmospheres,
Yeah,
right,
are they
are
reflective, I
so, like,
guess?
Venus?
It is Venus. Sorry, Hannah.
I wouldn't have
Hannah.
guessed Venus, so you're good.
Okay.
I can admit defeat.
And finally,
Because
what
Venus has all those clouds, and it's pretty reflective.
It's very
'cause of
bright.
that.
And
it is.
Yeah.
Yeah, makes sense.
Just look it up. It's the brightest one we see in the sky. I'm just kidding.
Its bond albedo is 0.76, so it's actually quite close to Enceladus in reflectivity. Yeah.
Huh. Okay.
What is the bond albedo of the moon and the object we were just discussing, Arrokoth?
Oh.
How reflective?
The
How much
moon is
light do
like
those two objects reflect?
0.3 or 0.4 or something, isn't it?
I'm going to go 0.6 for the moon.
The edge is to Addie, but you are both way off.
Oh.
0.11.
Okay.
Hold on. Which one?
Moon.
For the moon. Yeah, it's real dark.
0.11 is the bond albedo. Now that's a global average, right? So there's obviously variations to the albedo.
What's it on the near side versus far side?
That I don't know.
Oh.
But just looking at it, you can see. What about Arrokoth, the object that we were just discussing in the Kuiper Belt? What is its reflectivity? Do you think it would be higher or lower?
I'm going to go lower.
Why?
Because it's super fluffy.
Oh, okay. Interesting.
I'm thinking it's going to be scattering everything.
Well, scattering is scattered is counted.
Yeah.
Right? It's whether it scatters it or absorbs it. It's
the
question here. So
okay, I'm still going to go lower.
Yeah.
I'm going to go 0.25.
It is higher being icy.
I know nothing.
Yeah, 0.21.
Oh, I was close.
Yeah, you were close. But it's worth, when we look at the moon, it's like, oh, that's bright.
Yeah.
First, you got a crazy bright sun shining on it, and there's nothing else up in the sky that's anywhere close to that big or bright. But it's not super reflective, and a lot of objects in the solar system are, Hannah, much, much darker, such as Comet 67P and all those things. So it's not a crazy thing to guess that Arrokoth would be darker, but as Addie was mentioning, because it's much less processed object, still, whereas like 67P is an icy object that's had the outer layers of ice have been sublimated away and you're left with all the dirt left over.
Yeah.
So like dirty snowbanks are super dark.
In hindsight, it makes perfect sense.
Both the right answer and the wrong answer both make perfect sense in hindsight, which is just the way we like it. Yeah.
Soothing my ego.
While it may have felt like waiting for planetesimals to accrete, it was just another episode of Walkabout the Galaxy. Give us 5 stars and we'll give us the universe. Be sure to follow us on Facebook and Instagram to get all our updates and check out our YouTube videos on YouTube. Our videos now feature chapter markers so you can skip to the trivia answer if you're confused by the trivia question. Catch up on old episodes wherever you get your podcasts. Follow us on Twitter
at walk_the_galaxy.
And ask us questions anywhere using hashtag AskWTG. Our theme music was composed by Richard Jerusik. Production assistance is provided by Logan Basinger. Thanks to our listeners in Bavaria and around the world. Stay safe. I'm Josh Caldwell.
I'm Addie Dove.
And I'm Hannah Sargent.
We're the Astrocorps, signing off until the next episode of Walkabout the Galaxy.
Mordor.